All right, ready for some more runtime? So before we can compare and contrast Prim's and Kruskal's algorithm and talk about their runtimes, I want you to try and figure out the runtime for Kruskal's algorithm. So here's some pseudocode, and basically what it does is we create a list of edges. That's where we're going to store the MST. We then create a priority queue of edges, insert all of the edges so that they're sorted by weight. We create a weighted quick union with path compression to track connectedness. And then as long as there are more edges to consider, and we don't have a full MST, we're going to take the best edge. We're going to see if the two vertices on either end of the edge are already connected, and if they're not, we'll union them in the quick union object, and then we'll add that edge to the minimum spanning tree. So given this code, which is just basically a repeat of the conceptual picture we have so far, I would like you to figure out the runtime assuming that priority queue operations take log v time, big O log v, and that the weighted quick union operations, they take big O of log star v. So give your answer in big O notation. I'll be waiting here, and then I'll give you my answer. Okay, so my answer is that the overall runtime is E log E. And the way it works is that the number of inserts is going to be exactly E because we insert all of the edges, and each of those takes log E time in big O notation. Now deletions, not every edge is necessarily deleted because we might finish the MST more quickly, so I'll just call that big O of E, and each of those takes log E time, so that's E log E again. When it comes to the union and is connected operations, well, in the worst case, we are going to do v minus 1 union operation, so around v, but it may be the case that there are actually very few edges, so technically speaking, this might not be actually v, but not really that important, but it's big O of v. And same deal with disconnected. In the worst case, we're actually going to go through and check every single edge, but you may end up quitting early if the spanning tree gets finished early. So I'm using big O here instead of an exact count. And so overall, the runtime for cumulatively for each for each type of operation, they are respectively E log E, E log E, V log star V, and E log star V, because each of these is just the product of the number of times and the time per operation. Now, one little tiny fact, you can actually optimize this top step to take only big O of E time. In the heap sort lecture, we discussed this, but not here. But as the code is written, it's going to be E log E. Now, that means the overall runtime of Kruskal's algorithm is just going to be the sum of all of these. So we add these all up, E log E dominates, and so the overall runtime is E log E. Now you can actually do a little better. If we use a pre-sorted list of edges instead of a priority queue, that is, somehow the graph just provides as part of its API all of the edges in sorted order, you don't actually need to do this insertion deletion business. So if you have a slightly different graph API, the only operations that we need to do with data structures are based on union and is connected. And in that case, the overall runtime would be big O of E for the iteration through all the edges, plus the union and connected operations, so V log star V and E log star V, and in that case, the E log star V term dominates. Okay, so let's compare and contrast the runtimes of our algorithms. So we had Dijkstra's and Prim's, and so this lecture is just about minimum spanning trees, but I'm including Dijkstra's here because these two algorithms are basically exactly the same if we implement Prim's in the way that we described in the practical implementation part of this lecture. So their runtimes are both E log V. Now, Kruskal's algorithm is just a little bit slower at E log E, but on a practical basis, the difference between log E and log V is going to be completely negligible. And so I'd say maybe you give a tip of the hat to Prim's, but maybe Kruskal's is a little easier to implement. Okay? Now, if you have a graph that has the ability to provide you with a pre-sorted list of edges, in that case, Kruskal's algorithm actually gets a slight advantage because now it's log star V. Remember that log star is the iterated logarithm, so this is a value less than 5 in our universe for any graph. So that overall runtime is going to be just a little faster. But again, on a practical basis, all three of these algorithms are about the same. Now you can actually tighten this bound a little bit because the runtime of path compression based weighted quick union objects is actually based on the inverse Ackermann function, but I'm going with log star for consistency with our optional textbook. So I mean, it's still true. It's a little bit of an overestimate. So you might ask yourself, given these different minimum spanning tree algorithms, which one should I use? The answer is really any of them. They're fine. But maybe if you're somehow more, mathematically inclined, or if that's something in your heart, you might ask yourself, could we do better than E log star V? And so we'll talk about that in the last and final video of this lecture.